So I'm going to talk to you about more than just black box impossibility results. I want to focus on instead like limitations to constructing non-malleable codes, or the existence of non-malleable codes in some cases. So this, better. So this is joint work with Tal, who's here, and Dana Document-Saled and Mukul Kulkarni at UMD. Right. Non-malleable code, hopefully most of you are familiar. So what is it? It's basically a brittle way of encoding information. So you take a message X and you encode it and you want it to be tamper resilient. And so a non-malleable code is an encoding scheme, and it should have this sort of weak correctness guarantee where if you don't do anything, then you can recover the information. So it's non-trivial. And it should have this sort of security guarantee where either you recover the original message that you started with when you decode, or you recover something completely unrelated. And sort of like this event of whether the information is destroyed or not should also not leak anything about your message. Okay? So how can we formalize this? Non-malleable code, we can formalize this as via this sort of simulation argument. So you have a simulator for any tampering function f that you would apply to your encoded message. We would have a simulator, and the simulator doesn't take in any inputs, despite the sort of way things are represented here. It just like flips some random coins, and will either output this special symbol same or something in the message space, C. And then we'll wrap this simulator with a message. And we will replace any occurrences anytime the simulator outputs same with this message. And we want that these two this real world experiment where you're tampering with the encoded messages should be statistically indistinguishable from this simulated experiment. Okay. Another way of formalizing this is you can say that this real world experiment should be close to some distribution over identity and constant functions. For me, this is easier to think about, but I don't know. Whichever you prefer. It doesn't really matter too much. Right, and just for some notation, so k is going to be the length of our messages here. In general, we don't always need to restrict ourselves to this Boolean alphabet, but in general, k symbols come in and come out. Epsilon is going to sort of correspond to the distance between these two distributions. Is sort of the security guarantee here. Okay? And for the particular case, and this is going to be useful for us, for the particular case of when you want to just encode one bit, we have this really nice characterization of non-malleability where, right, it's just basically your advantage in flipping the bit of a random encoding. So I sample a random message, I encode it, and right, epsilon should be some upper bound on your advantage in flipping the encoding when it's decoded. And decoding to the opposite bit. Okay? Does this make sense? Good. Okay, so right, lower bounds. What is infeasible here? So sort of a sanity check. We can't hope to achieve non-malleable codes against the class of all tampering functions, right? Because there's always this trivial attack where you simply take any non-malleable code, you just decode, flip a bit, and re-encode. Great. And in fact, you can think about this a little bit more. If this encoding scheme is efficient, then right, this stack is also efficient, right? Decoding is efficient, flipping a bit is easy. Re-encoding is efficient, so you can't have any. So you can't have any efficient codes for the class of all efficient tampering functions. Great. I'd like to. So that sort of gives you some intuition for what's impossible. I'd like to sort of shift gears. So oftentimes non-malleable codes are introduced as a relaxation of error correcting codes. So unlike error correction, you don't care about like recovery. You only recover in this sort of like trivial case. And it's sort of presented like we make this relaxation so we can have guarantees against a much broader array of channels. And oftentimes this is stated sort of as saying like as a consequence we can handle tampering that changes many more symbols than is possible in error correction. And so while this is technically true, right, yeah, it seems to say that we can handle non-malleability for the class of functions that change, say, the d over 2, where d is the minimum possible distance for, say, your parameter, your alphabet sigma, and your parameters k and n. Seems like this should be possible, given this statement. Or maybe it's, yeah, I don't know. But it's not. So our first result is that you can't have non-malleable codes for this class of functions that change.
So non-malleable code is randomized?
Yes. I'm saying the distance of an arbitrary code in this sort of space. Encoding.
Not necessarily related to the non-malleable.
Yeah, exactly. It's sort of just a lower bound on distance for, like, right? Okay. For more than 2 messages. That's a good point. Thank you. So how do you go about proving this? So the first is I'm going to claim that there exists some special message x such that for every code word that, right, this encoding scheme is randomized. And so, right, x has many code words, as you mentioned. And for every code word, there's something in the code words, in the space, in the channel space where, so there's near every code word, there's something nearby that doesn't decode correctly. Yes?
Can you recall what is
ft over d over 2 is this function, is the class of functions that change at most d over 2 symbols. I'm not specifying d explicitly, but you know, think whatever. You can think n over 2, for example. Okay? So, right, every code word corresponding to x star has something nearby that does not decode correctly. Okay, so it's sort of like this picture. These red dots are these x star code words, and there's things that decode to other colors nearby. Okay, so why is this, yeah? All possible settings of randomness. So in this setting, right, so, okay, what does this mean? C in E of x star, is this what you're asking? Yes, so fix all possible random strings and see what pops out. Okay, so, right. So what is the proof of this? Suppose this is not true for every possible message x. Then you take something that is the minimal distance, and right, there's this point exactly in the middle, which is d over 2 from each. Right, these points will form a code. And there's something in between, which, you know, you claiming decodes both to 2 different things that are distinct. Okay? So easy sort of visual proof. Hopefully it makes some sense. And so how are we going to attack? We're going to just attack this message x star. So, right, whenever we see, we're going to look at the entire code word. The tampering function is going to look at the entire code word. It's going to check, is it some encoding of x star? And if it is, it's going to output this point nearby that's where it only needs to change d over 2 symbols that decodes differently. And otherwise, it won't do anything at all. Okay? And the point being that because, so what do we notice about this tampering function? The simulator can't output same because on x star, it's never x star. Right? Any time it outputs an x star code word, you output something that decodes differently. So the simulator can't ever output same. And there's also some other message that because we're going to take the message space to be like slightly non-trivial. So there's going to be some other message that doesn't occur too frequently. Like it can't always decode to something else. So you can't just put out this constant message. The simulator can't output this constant message y star all of the time either. But if you look at how this thing the experiment will behave on y star, it will always output y star. So the simulator is stuck, and you can't have a non-malleable code. Okay. Hopefully that made some sense. So then I'd like to sort of shift gears. So a lot of work in this space on non-malleable codes has been done in getting explicit codes. In particular, an explicit for me really means more efficiently computable. And you can sort of point to a specification. Okay? So, but one thing you can observe is that the non-malleable code for class F, assuming this class has some weak composition properties, in fact implies an explicit average case hardness bound for this class. Okay? So take ED, some 1-bit non-malleable code for this class F. What is the hard problem that you get here? It's the decoding function. And what is the hard distribution? It's just encode a random message. Okay? And why is this hard? Because, right, basically, if you could solve this hard on average problem, then you use your slight advantage and you just output fixed code words that will decode to the opposite thing, to flip the bit. Okay? And so this sort of gives you some indication that you can only hope to get unconditional results for very sort of limited classes of tampering functions, at least in the computational regime. Yeah, but it also seems to suggest something else possibly, or maybe not. Maybe it's obvious to you that these things are very different. But it also seems to, are these two notions in fact equivalent? So is average case hardness, in fact, does it imply non-malleability? And so we have some sort of evidence sort of suggesting this. So with Tal, many of the authors on this work, and also Rachel, we have some frameworks for sort of transforming average case hardness modulo some cryptographic assumptions and de-randomization style assumptions into non-malleable codes. There are also, we have explicit constructions that work using explicitly these average case hardness proofs for specific classes. So you might think maybe there's something to say here. Unfortunately, no. But this is also, it sort of makes sense. Non-malleability seems like a much more structured thing. And it just seems to say that these, for example, these proofs of average case hardness are just much stronger than people are actually using. So here's an example of something that violates this conjecture. So an L local function. So here's the dependency graph of some function f. So on the left, you have the input bits, and you have the output bits. The dependency graph, you have an edge from the left to the right if the corresponding input bit affects the output bit, right? And L is some upper bound on the degree of the right, okay? So it says like any output is only affected by L inputs. So right, it's easy to see that n-1 local functions have no advantage in computing the parity function. Great. But the second result that I'll talk about is that there's no non-malleable code for the class of local functions that's the even n-log n local functions. Okay? I'm going to present for n-1 local functions instead, but it's not too difficult to generalize. So what I want you to first put in your mind for how this works is keep this experiment. Okay, so we have this encode a random bit. Don't change the first n-1 bits, and then just ignore whatever's the last thing, put something random inside, and decode, and see what comes out. Okay, so you can define this experiment. And there's sort of like two cases that will happen, that you can have happen here. And one is that B tilde is the same, agrees with B with high probability or reasonable probability. And we can use this to attack the function, okay? So first thing, what is our tampering function going to do? The first thing it's going to do is it's going to run basically this experiment. It's going to compute B tilde. And why can it do this in locality n-1? Because it's completely ignoring the last bit. It looks at the first n-1. It has its own random bit in its pocket, and it runs the decoding function. Because it's computationally unbounded, whatever. And it outputs some fixed code word that decodes to the opposite thing. Same sort of trick as before. Okay, so this will tamper successfully, give you some advantage in flipping the bit, the encoded bit. So the second case is that these things are not equal with some probability, okay? Some probability bounded away from 0. So what do we do here? We just flip the last bit. Why can we do this safely? Because if the last bit is unchanged, then we know by the correctness of non-malleable codes that you will just recover B. So because we know that in this experiment with random code words that some percentage of the time like things are flipping, right? It's bounded away from 0. This means that if we flip the last bit, you will recover the opposite thing perfectly every time, okay? So this gives us a tampering attack for the other case. Okay, so in either case, we can attack this function. And you can extend this to log n, n minus log n, instead of just n minus 1. It's a bit more work. Okay, but I know that this is probably not, I don't know, I'll be reported, I guess. But I'd like to spend a minute just reflecting on this theorem 2 as an upper bound. Here, so right, if you look at the actual proof, and actually the extended proof that I'm not presenting here, what you have is actually a specific family, not all these local functions, but a very specific family. Like the second class function I showed you is like a really small function family, but the other one is quite relatively large, but not very large. It's relatively small. Has size at most, like if you take log of the function family, it's n minus log n plus 1. Okay? We have very strong feasibility results for non-malleable codes that say that if you want, you can interpret this if you want something that's 1 over n non-malleable, which is maybe not very useful for practice or something, but in theory it's interesting, then there's like existential constructions for any tampering function such that it meets this bound. It's slightly smaller than n minus 5 log n, or log of the size of this class. Any class like this. So it leads you to one to ask, this is, I guess, an open question, is like, what is the smallest family for which 1 over n non-malleable codes do not exist? Or put in a different way, like, how strong do you think like generic existential results how strong can these existential results be? Yes.
The top part is just that you don't read k bits, and therefore you can get them with probability 2 minus k.
Yes.
In this case, algorithm, then you have 1 over poly success, and since your definition talks about negligible, then 1 over
We're talking just about 1 over n.
No, but since the definition of non-malleability here you insist on negligible, although some of the construction get 1 over poly, therefore even if you win with 1 over poly, you violate the bias. So
That's true.
It seems that for any epsilon, they put the real epsilon in distinguishability, we'll be able to save log over 1 for epsilon or something like 2.
I'm not totally sure. I think that, right, the upper bound will weaken if you, yeah.
It's kind of, it seems for, I don't know, like
So typically, I mean,
it's an artifact of the definition in a sense, right?
Sure.
right, I mean, typically this factor of log
Sure.
n has a log 1 over epsilon in it, right? Or 2 log 1 over epsilon. So maybe it's not the correct term for the error 1 over n.
Okay. Okay. So I'd like to talk about explicit codes, like constructing explicit codes via assumptions. Oh, okay. So right, so now I'll try to blaze through the black box part. So we have explicit constructions for NC0 and AC0. It leaves open the question, can we construct explicit codes for NC? Okay, so right, we already went over the fact that non-malleable codes imply this average case hardness. And so in fact, if you had an efficient non-malleable code, the decoding function would actually separate, by the same argument, would separate P from NC. Okay? But so you can ask those, so suppose we just assume that P does not equal NC, or suppose even more this, we assume some specific language is hard on average for NC. With respect to some efficiently samplable distribution, can we hope to get an efficient code? Right, so L is hard for NC. Can we get to some efficient code that takes in this language? This is a non-malleable code for NC. And so we have some sort of partial answer, yes. You can get such a code via this framework, but it's in the CRS model and it requires some more assumptions. What if we want to get rid of the CRS? Okay, so our third theorem is the black box, which says that there's no black box reduction from a hard on average problem for NC to a 1-bit non-malleable code for NC. Okay, what is a black box reduction in this scenario? So what sorts of proofs are we looking at? What sorts of proofs are we trying to rule out? So we're trying to say, rule out proofs that work by reduction, where the reduction is such that if there exists some, right, you want to say, like, if there is some tampering function in this class F that we want to rule out the reduction for, then somehow the reduction that's given oracle access to this tampering function violates this assumption. Okay? In particular, we say that R is a F black box reduction if, right, it's black box. So it should, R of F should solve the hard problem just based on the fact that F breaks the non-malleability, regardless of whether it's efficient or not, in this class F or not, I guess, yeah. And second, we want that the reduction is essentially meaningful. We can use it to say something about this underlying problem. In particular, if F is in this class, then we want that R that has access to F is also in this class. And so unlike this sort of standard setting of black box reductions that Puli was talking about, here it's a bit trickier because we're looking at these low complexity classes that don't always compose very well. And so you need to be a bit careful about all of this stuff. But so how does this work? So hopefully I can get through this. So right, the idea, right, we're going to use this sort of meta reduction technique. And the idea is that if you have such a reduction, right, it's already too strong and actually basically solves the problem yourself. So here we have R, it's reduction. It takes in some instance from this supposedly hard problem. It queries this tampering function or a bunch of tampering functions, but here's just one with code words, receives tampered code words back. And after, you know, T queries and some other stuff, whatever it does, it outputs some answer Y. Okay? That should agree with this language of high probability if the reduction works. Okay? So we're going to start with this inefficient tampering function, as you might expect. So that on input C, it's just going to, that decodes to B, it's just going to output a code word, a random code word for the opposite bit. Okay, and we're going to, you know, hybrid our way down to a stateful tampering function that's going to have all of these random tampered code words, just totally random tampered code words, hard-coded inside of it, basically. And every time it receives a query, it's going to look and say, did I see this before? If it saw it, it's going to output whatever it said last time. And if it didn't, it will output something, just the next thing in the list. Okay? And the point being that, right, because this data structure of looking things up can be computed efficiently, you can compose this whole thing, and the resulting thing will be in NC, and will just break the problem, the underlying problem for you. Okay? Why can you compute this lookup table efficiently?
Yeah, without editability. I mean, so maybe I didn't get it. You get a query.
You don't bother checking what it decodes to. Is this what you're asking? You don't check at all. You just output the next random thing in the list. Okay? The hybrid argument is going to say that we can do this, and that the output distribution won't change. And why is this the case? So right, you'll just, what we're going to do is we're going to transition, of course, from the stateful tampering function to the, from the random one to the stateful one in order. So you're going to use this stateful thing where everything is totally random. And right, you'll have like two hybrids that only differ on one query, so you can basically ignore everything else. And the point being, because they differ, one is like decoding to the opposite bit, giving you something that's the exact opposite, and one is giving you a random code word. And this basically gives you a distinguisher for when you're encoding B or not. And you can use this to break the non-malleability of the code. Okay? So you proceed through until you've transferred over to this the stateful tampering function that compiles nicely, and you can rule out this kind of reduction. Okay, there's a ton of subtleties here that I'm ignoring. There's all sorts of security parameter issues that you can leverage, and we have some solutions for some of the time. But I'm going to continue sweeping that under the rug. Where does this really fall apart, like completely? Because we have some solutions to these. So it really falls apart. Okay, A, if you can't implement the data structure, I don't have that here, but so that's very low complexity classes. If also, it doesn't work if you start with a harder language, a harder distribution problem than your non-malleable code works for. And perhaps more interestingly, if you start with hardness of compression. So I guess I don't have time to say what this is, but basically if I can't output a slightly shorter string that's somewhat correlated with L of X, then this reduction technique doesn't work for these sorts of hardness assumptions. Okay, so yeah, I'll stop there.